welcome to another lecture session of Introduction to Astrophysical Fluids. Previously, we introduced the effect of rotations in several astrophysical fluid flows, and first we distinguished between the solid body rotation and differential rotation. Then also we showed that under certain criterion a system can sustain a differential rotation, and we call that Rayleigh's criterion of stability. Okay, and then also we showed that it is very important to study the hydrodynamics of a system, for example of an astrophysical system, with respect to a rotational frame of reference. For example, that's very important for us because we are living on Earth, and if we observe something, so either on the surface of Earth or we study something exterior to the Earth, in both cases we are studying the system from a rotational frame of reference, right? And of course, from a non-inertial frame of reference. Of course, when we are talking about the studying something which is taking place outside Earth, this is not really, the effect is a bit complicated to take in. But if something, let's say we are trying to study the dynamics of fluids which we can see on the surface of Earth, for example the oceanic motions, the atmospheric motions, it's true that they are not in true sense astrophysical fluids, but these are important things because many planets can have atmosphere. If not normal fluids, many stars can have fluid which are actually of plasma nature, but at the end of the day, the fluid dynamics and the investigation of the fluid dynamics is important from the with respect to a rotational frame of reference. That's for sure true, because whenever let's say we are trying to see the dynamics of some plasma. Okay, I have not yet introduced plasma, but plasma can be regarded as a fluid, and if we want to see the dynamics of the plasma on the sun surface, let's say the plasma almost behaves like a neutral fluid, a normal fluid. Okay, then also sun is rotating, so if we assume that someone is sitting on the sun, it is then if we know how should the equations look like with respect to a non-inertial frame of reference, then we can easily, without going there, of course you know that we cannot reach on the surface of the sun like that, so without going there we can actually we could know what should be the conclusion of an observer who is sitting on the surface of the sun. So this type of things are of course there. So and the same thing can be applied for galactic fluids as well. If someone is sitting on the galaxy, for example, and it is rotating with the same so for example, let's say we belong to Earth, that's true, we belong to solar system, that's true, but we also belong to a galaxy. It's a Milky Way. Now, if the galaxy is rotating, somehow we are all supposed to be, to be subject to that rotation. So, due to that rotation, also, whenever for example, we are measuring something from here, this effect is also can be effective. So, so some galactic effects, for example, okay, if we try to study and conclude, then this type of thing, how important can that be? Okay, how important can the role of non-inertial frame of reference be? That can easily be understood from this study. Okay, so with all these things, we actually already discussed the importance of discussed the aspect of the astrophysical fluid dynamics with respect to a non-inertial frame of reference, which is rotating with a speed omega, okay, with an angular speed omega. Okay, so in this lecture, what we will try to do is to search for some interesting properties, and we will see that I mean, already we have investigated several properties of real fluids and in ideal fluids, okay, in previous lectures. So now we will see in this lecture a very important theorem which we discussed some weeks some weeks earlier, that is the Kelvin's vorticity theorem, or the frozen-in theorem. How could that be modified if we are studying the whole system with respect to a rotating frame of reference? Okay, so of course here we will investigate systematically what will be the generalization of Kelvin's vorticity theorem in a rotating frame. Okay, so we investigate that whether this this Kelvin's vorticity theorem or the frozen-in theorem remains the same, or it has a different form if we sit on a rotating frame which rotates with an angular speed omega. At this instant, I am not saying anything on the constancy of omega. Omega can be anything. For example, it can be variable, it can be of course omega is the angular speed with which the system, the reference frame is rotating, so it can be a function of time as well. But just for instance, we just take this can be anything. Okay, it can be constant, it can be a function of time. Okay, now for the whole treatment, we will just constrain ourselves in the in the case of incompressible fluids with negligible viscosity. That means incompressible and ideal fluids. And now you know that maybe incompressible fluid is not a very reasonable assumption for galactic or interstellar medium, but at least for oceanic fluids and atmospheric fluids, incompressibility is certainly a good approximation. And ideal fluids are is a very reasonable approximation for most of the astrophysical fluids. And so if we just remember that what was the form of Kelvin's vorticity theorem for an ideal and incompressible fluid, we can actually simply write that this is nothing but del omega del t is equal to curl of v cross omega was the general form of this the equation which should be satisfied for a quantity whose flux to be conserved in time, right, with a fluid element. So that was the frozen-in theorem. So frozen-in theorem simply says that if we have a vector field omega which satisfies this type of partial differential equation, okay, where v is the fluid velocity. Okay, omega can be anything. Here omega is eventually equal to the curl of the velocity field. Okay, and if this is true, then ddt of integration omega dot ds will be equal to 0. That means the flux through any surface, okay, the flux through any surface along the trajectory of a fluid particle, okay, that's why this ddt appears, will be constant. That means ddt of this term will be 0. So that was the statement for frozen-in theorem. And we said that, for example, if this is the vorticity line, so that is the circulation is actually something which is conserved in a fluid, in an ideal incompressible fluid. And actually we also showed that this form is true for not only ideal incompressible fluid but also for ideal barotrophic fluid as well. Here we are just we are happy to see the case for ideal incompressible fluid. Okay. Now here you can actually see that if you remember just what we discussed in the previous lecture, that with respect to a non-inertial or rotating frame of reference, the equation of the momentum evolution should be written in this form, del V del T, and this V dot nabla V, that is the advection term, should be always written like this: gradient of V square by 2 minus V cross omega. And here you can see this minus V cross omega is here, and this term is going to the other side. Okay, so here, so minus gradient of V square by 2, and so you can see that this is the pressure gradient term. So since we are taking incompressible fluid, so rho comes inside the gradient operator, and this minus gradient of phi is nothing but the potential due to the body force, which is conservative. For our case, it can be gravity, for example. And if you also remember, this is nothing but the centrifugal acceleration term. Okay, so which can be written as a gradient form as well, minus gradient of half omega square. So this is minus gradient of minus half omega cross r whole square. Okay, so the final one is the representative of the so-called Corioli term. Okay, so the Corioli term is becoming non-zero, or becoming actually comes into play when V is non-zero. Okay, what is the meaning of V? V is the fluid velocity with respect to the rotational frame of reference. So V is the relative velocity between the rotational frame of reference and the fluid flowing on it. Okay, for example, if we just consider an ocean is flowing, so the velocity V is nothing but the linear velocity with respect to the linear velocity of the ocean with respect to the earth, because due to rotation earth also has some linear velocity. Okay, and V is the relative velocity of so the vector subtraction of these two. Okay, so if V is 0, so for example, if something which is static on the earth surface, so it is rotating on with earth, but it is static on the earth surface, with respect to earth this is static, then the Corioli force will be 0. Okay, but here this is non-zero, and so finally you can see that if you take the curl of the whole equation, finally this will give you del omega del T is equal to so this term will be brought to this right hand side, so this will be curl of V cross omega. So curl of the whole gradient will vanish, because curl of a gradient always vanishes, and minus 2 times omega cross V. Okay, so this will also be taken inside the curl. So now I have just changed the sign from minus to plus, and I wrote it as plus curl of V cross 2 omega. Okay, so I just changed the order here. If we can do that, then finally we can say that this is equal to del omega del T is equal to curl of V cross. Then actually you have same type of term, and you can take curl of V cross omega plus 2 capital omega. So this is something which is a new variable which comes into play and which satisfies the so-called equation necessary for the Frozen-in theorem. Okay, and now we talk about the constancy of omega. We talk about the constancy of omega. So if omega is constant, then one can simply write that we can actually take this del omega del T is nothing but equal to del T of omega plus 2 capital omega, because capital omega doesn't have any explicit time dependence. So del capital omega del T is 0, so I can add some 0 over here without any problem. So the final equation should look like very looks like very elegant, and it is now saying that it is not omega but omega plus 2 capital omega, which is practically satisfying the equation necessary for the Frozen-in theorem. And this is known as the generalized generalized vorticity theorem or Bjerknes theorem, who gave this theorem and actually proved this theorem in 1937. Okay. Now, from this equation, what is the first thing you can see, even from this equation? Now, if you remember this form, if I said that, I mean, we also discussed that if the initial vorticity is 0, okay, then del omega del t is 0. So, if the initial vorticity is 0, then del omega del t remains to be 0 and del omega del t is 0 and omega remains to be 0. So, for an ideal and incompressible fluid, if the initial vorticity is 0, the fluid is actually an irrotational flow as well. Okay. Now, is it the same case for a fluid with rotation? The answer is no. Because if your initial velocity, vorticity is omega is 0, you still have this 2 times capital omega, which is there. So that will give you a finite non-zero del omega del t. So even when your initial vorticity is 0, just due to the global rotation, okay, because you are I mean, just due to the rotation of the frame of reference, basically not the global rotation, sorry, okay, because you are seeing or studying the system with respect to rotating frame of reference, due to your rotation, basically the system will develop some vorticity inside it, and this is exactly the thing which happens when you are studying in some laboratory experiment, some fluid dynamics experiment on Earth. Because, and if the so for example, I mean, on Earth, sorry, in a rotating system, okay, of course the rotation, of course, as we saw that the effect of the rotation of Earth is negligible in this case, so that is not the thing. But what I am trying to say, that if you make a setup where the setup is rotating with an important omega, then even if the initial vorticity is absent, then with time you will see that inside the fluid you can see the vorticities to be developing. Okay. So, that is a stark difference between the normal frozen-in theorem and this frozen-in theorem for the case of rotating fluids. Okay, so now you see that from a rotational frame of reference, then what happens, that the vector omega plus 2 capital omega satisfies the frozen-in theorem. So now what is the meaning of frozen-in theorem? That means ddt of integration omega plus 2 capital omega dot ds is equal to 0. So the flux, surface flux of this quantity will be 0. Will be constant or will be invariant in time. Of course, if we are following the trajectory of a fluid element, because this is, once again, this is Lagrangian derivative, right? Now, from equation 1, so this equation, from equation 1, one can see that even if the initial fluid vorticity is 0, the fluid will develop vertical motion by virtue of omega. That we already have discussed. Now, the second point is very interesting, that if the fluid is not rotating relative to the frame, but by some means locally this fluid is squeezed to spread in a thinner layer, then what happens? Then of course its area will increase, and if its area will increase, then I mean, if the fluid doesn't have some, I mean, considerable vorticity on its own, then this thing will approximately be nothing but integration s 2 times omega dot ds. Now if your total area increases, then this flux will also increases, right? This flux will increase, so this one increase, and till now there is no small omega, but we know that ddt of integration omega dot ds should be 0, right? And that is true for the fluid element, right? Because that is true, because at that point there is no omega, there is no small omega. So this should satisfy the I mean, frozen-in theorem. And if this is true, then the system should develop some small omega, so that the small omega practically opposes this capital omega to keep this 2 omega plus small 2 capital omega plus small omega dot ds integrated over s is conserved, along the trajectory of a fluid element in time. Okay, so this is, so this is what I am trying to say, is that just because due to this generalized Bjerknes theorem or generalized frozen-in theorem, you can actually see that the system should develop some omega by the virtue of this omega. Okay, so this is exactly the mechanism by which very frequently cyclonic storms are produced in Earth's atmosphere. Okay, and actually, to be very honest, this is not only the case of Earth. In planetary atmosphere, in stellar atmosphere, sometimes this type of things are forming. Okay, a very simplistic behavior can be explained. Explanation of this behavior can be done using this type of analytical tool. Okay. Now, in astrophysical context, is this important? Yes, because in rotating stars may produce also local cyclones on their surface. So that's exactly what I said. Okay. So this is also a very interesting domain of research. You can again see over internet the papers and the ongoing research works on this topic. Okay. Now, after this topic, in the second part of this discussion, I will just, I could have divided the whole discussion in two parts, but this Taylor-Proudman theorem is almost very much linked with the previous discussion, so that's why I am just doing this in one single lecture. So we just have seen that for a rotational frame of reference, okay, when we are talking about with respect to a rotational frame of reference which is moving with some angular speed omega, the frozen-in theorem is true for this quantity. Okay, now we are saying, and because this quantity is satisfying something like d for dA dt is equal to curl of v cross a, this type of thing, where a is the concerned vector. Now if we consider a steady fluid flow, that means there is no explicit time dependence of the fluid flow, and we consider that in the rotating frame of reference, then what happens? We are always with ideal and incompressible assumptions, and so then we will have just this term will be equal to 0, this term will be equal to 0, so that means this term should also vanish, and that's exactly what I have written over here. The curl of v cross omega plus 2 capital omega should be 0. In addition, if we now consider flows where the fluid velocity and vorticity are small compared to omega, then you can actually neglect omega, small omega, with respect to 2 capital omega. That's possible if the flow is slow, not very fast, and with respect to the rotational speed of the reference frame. Then what happens? Then you can neglect this term, and you have finally this vector which is irrotational practically. So curl of v cross omega will be capital omega will be equal to 0. And if you now expand them, you will have 4 terms. So 3 terms will be vanishing. If you remember what they are, there you will have 2 terms like divergence of v omega with a minus sign plus divergence of omega with v, and both of them are 0. This is because incompressibility, this is because omega is constant. Okay, and there will be other 2 terms. One will be v dot nabla omega, which will be also equal to 0 because omega is constant. And finally, if you say that the 4th term which is rest, so it will be simply omega dot nabla times v, and so that will be equal to 0, so that the whole thing should be equal to 0. So this one is true only when we are talking of ideal, incompressible, slow and steady motion of a fluid in a rotating frame of reference. So many things: ideal, incompressible, slow and steady. So this thing is known as, this theorem is known as Taylor-Proudman theorem. Proudman gave it in the year 1916, and Taylor actually somehow, from the Taylor's point of view, Taylor contributed in the year 1921. So this theorem simply says that V does not change in the direction of omega, right? That's simply the case. If this is zero, that means this is the change in the direction of omega. This is the change in V in the direction of omega, the directional derivative type of thing, correct? And that is zero. That is zero. So that means V does not change. V is constant. Okay. So it simply says that parallel to the rotation axis, slow and steady flows, of course ideal and incompressible flows, they remain invariant. And what is the effect of that? For that, I will tell you something here by drawing. So let's say if you have a vessel and some fluid is moving. Okay. Now let me take this color. Let's say you have a small cylindrical capsule type of thing which is fixed over here. Now the fluid is when the fluid is steady, let's say the fluid is, first of all, is steadily developing. Okay, so there is no problem, everything is steady. So the fluid is just moving like a solid body along with respect to this direction. Okay, and this is the axis of the rotation. Now let's say there is no problem, everything is rotating with the same angular speed. Now let's say suddenly the fluid's velocity, angular velocity of the system or the container vessel is increased suddenly. So the water's viscosity is not that strong, so the water actually takes some time. Okay, maybe I have said water, I have not previously said water. The fluid is inside, does not have, let's say, very strong viscosity. So that's why the fluid will take some time, so that the solid body type of rotation again gets re-established. But between these two, what happens that this fluid will have some, the fluid is the fluid is very, very slow. So that means the vessel is assumed to be rotating with some angular speed omega, and with respect to this omega, with respect to this omega, the omega which is just developed inside the body because of the small perturbation is very, very small. Okay, and so that's why we can easily use Taylor-Proudman theorem. So Taylor-Proudman theorem says that parallel to this axis, the fluid flow nature will be always unchanged. Now let's say I have this obstacle over here, so the fluid will always try to skirt the obstacle here, but it is what can in general be expected, that the fluid which will be far from this obstacle will not be considering the effect of this obstacle. But it is seen that since this is parallel to the direction of the rotation, okay, and here in this part you have this type of motion, the motion is actually totally followed even when you are at a higher layer in the fluid. So finally you will see there will be a column actually, okay, the column even much more, containing much more higher layers. You can see the column which is rotating as if the obstacle is actually expanded up to this height. Okay, so this is the Taylor-Proudman theorem. So exactly the same thing sometimes the aircrafts they face, that let's say you have some obstacle, or you have some hill or mountain type of thing, and due to that they have some so this type of thing. And if let's say that due to the rotation or something, if the fluid just around this mountain or something is just rotating, okay, is just rotating, so this I mean rotating, avoiding the exact situation of the mountain, this type of rotation will also be continued when you are at a greater height of this mountain. So there will be an invisible column of influence of this obstacle, okay. But for that we need the system, the global system, to be rotating with a considerable high speed of rotation, okay. Speed means angular speed, of course. And here you see that this invisible column, which basically gives the effect of this obstacle, is known as the Taylor's column, okay. So that's why this thing is very important, both for geophysical fluids and astrophysical fluids, okay. In the next lecture we will discuss the shape of an astrophysical body, or a I mean astrophysical fluid, okay, under the effect of self-gravity and rotation, okay. Thank you very much.